In prehistoric times, very little was wasted. There were few people and lots of space. Most trash was biodegradable, so it wasn't really a problem, but some did leave its mark. Shell middens are essentially prehistoric landfills.
In the earliest days of human history, humans were hunter-gatherers, often moving from place to place in search of food. But about 10,000 years ago, our ancestors began to learn the secrets of selective breeding and early agricultural techniques. For the first time, people could raise food rather than search for it, and this led to the development of semi-permanent villages for the first time in history. Why only semi-permanent, you might ask? Well, at first the villages still had to relocate every few years as the soil became depleted. It was only with the advent of techniques like irrigation and soil tilling about 5,000 years ago that people could rely on a steady and long-term supply of food, making permanent settlements possible. And with the food surpluses that these techniques produced, it was no longer necessary for everyone to farm. This allowed the development of other specialized trades and, by extension, cities.
As populations grew and moved into cities, trash became a problem. It littered the streets, attracted pests, and bred diseases like the bubonic plague. Ancient Egyptians threw their garbage in the Nile, where they also bathed and got their drinking water. Around 500 BC, the Greeks established a law stating trash must be thrown at least 1 mile away from city walls.
With cities now producing surplus food as well as tools, crafts, and other goods, there was now the possibility of commerce and interaction over longer distances. And as trade flourished, so did technologies that facilitated it, like carts, ships, roads, and ports. Of course, these things required even more labor to build and maintain, so more people were drawn from the countryside to the cities as more jobs and opportunities became available. If you think modern cities are overcrowded, you may be surprised to learn that some cities in 2000 BC had population densities nearly twice as high as that of Shanghai or Calcutta. One reason for this was that transportation was not widely available, so everything had to be within walking distance, including the few sources of clean water that existed then. And the land area of the city was further restricted by the need for walls to defend against attacks. The Roman Empire was able to develop infrastructure to overcome these limitations, but other than that, modern cities as we know them didn't really get their start until the Industrial Revolution, when new technology deployed on a mass scale allowed cities to expand and integrate further, establishing police, fire, and sanitation departments, as well as road networks and later electricity distribution.
Solid waste management is a universal issue that affects every single person in the world.
Poorly managed waste is contaminating the world's oceans, clogging drains, and causing flooding, transmitting diseases, increasing respiratory problems from burning, harming animals that consume waste unknowingly, and affecting economic development, such as through tourism. Without urgent action, these issues will only get worse.
Right now, over 2 billion people don't have access to solid waste collection, and 3 billion people lack access to controlled waste disposal facilities. Solid waste management is an essential utility service for all. And wouldn't you wish for a clean, healthy, and pleasant planet to live in, where all have access to controlled waste management and disposal facilities?
Here's what everyone should know.
First, rapid urbanization, population growth, and economic development will push global waste generation to increase by 70% over the next 30 years. Each year, the world generates more than 2 billion metric tons of municipal solid waste. Without urgent action, this will increase by nearly 3/4 to 3.4 billion tons over the next 30 years. East Asia currently generates about 1/4 of the world's waste, while waste generation growing the fastest is in sub-Saharan Africa and South Asia. While high-income countries account only for 16% of the global population, they generate over 1/3 of the world's waste.
Did you know that each person in the EU generates 475 kilos of waste each year? Overall, 26% of municipal waste is sent to landfill, 27% is incinerated, and only 47% is composted or recycled. This means that 80 million tons of recyclable materials are thrown away or wasted annually. Bio-waste, and especially food waste, is the most sensitive fraction because of its potential recovery as energy or nutrients for soil, but it is currently separately collected only in a few member states. About 75% of food waste may be avoidable.
Second, in low-income countries, over 90% of waste is mismanaged. It is either openly dumped or burnt. Upper middle and high-income countries provide nearly universal waste collection. In high-income countries, more than 1/3 of waste is recovered through recycling and composting.
Trucks deliver waste cardboard, paper, plastic, wood, certain metals and so forth from industrial and municipal collection streams to sorting centres, where we weigh, store and feed them into the sorting line. Certain types of waste, for example waste electrical and electronic equipment, follow specific treatment circuits. First, we separate waste by size in a trommel screen, which is basically a spinning drum. The large and small waste is sifted out, then treated. Then most of the waste reaches the next screen, which separates it according to its density and shape. The flat waste heads up, and heavier hollow waste heads down. An overband magnetic separator lifts all the waste that contains iron. An optical sorting head then separates waste according to its material. Here, a scanner analyzes the waste that travels through its light beam, and compressed air blasts eject the waste that contains the material we want to extract. Then, several optical sorting heads separate the other types of waste, different types of plastic for instance. We use our self-adapting sequential sorting system instead of a full battery of sorting heads. This machine sorts waste in loops, according to the predominant material that the scanner detects on the belt. Operators then check the automatic sorting. They use innovative remote sorting capabilities to eject unwanted materials simply by tapping a touchscreen. The sorted materials are compacted into bales and inspected carefully for tracking purposes. Manufacturers can then use them as raw materials to make new materials or new products, which will be used, reused and recycled again and again.
Once trucks arrive, they are weighed and checked in before heading inside to the tipping hall. The waste is unloaded onto the tipping floor and visually inspected for any unacceptable items, which are removed for separate recycling or proper disposal. Waste is then pushed into a storage pit and thoroughly mixed before being loaded into bins, which we call hoppers, where it travels to the combustion chamber. The tipping and waste storage areas are maintained under negative air pressure to contain dust and odors. Once fed into the combustion chamber, waste is combusted at extremely high temperatures in a self-sustaining process at approximately 2,000 degrees Fahrenheit. A typical hopper load is completely combusted in 1 to 2 hours. As waste is burned, the heat converts water in the steel tube-lined walls into steam that rises through boiler tubes where it is superheated. The steam turns a turbine-driven generator to produce electricity, or may sometimes be used directly for heating or industrial processes. The electricity produced by the turbine generator is exported to local utilities for use in homes and businesses. Each ton of waste can generate 550 to 700 kilowatt hours of electricity. Steam from the process is condensed back into water and returned to the boiler tubes, making it an efficient, closed-loop system. After combustion, the volume of waste is reduced by 90%, leaving an inert ash and metal. Remaining ash is beneficially reused or landfilled as non-hazardous waste. Ferrous metals such as iron and steel are recovered using a rotating drum magnet, and non-ferrous metals like aluminum and copper are separated by an eddy current system. Collected metal is sold to be made into new products. State-of-the-art air pollution control equipment ensures that emissions are well below limits to be fully protective of human health and the environment. We neutralize acid gases using lime in a scrubber reactor and inject activated carbon for heavy metal control. We control emissions of particulate matter primarily through a bag house, which employs thousands of fabric filter bags. All flue gas must pass through the bags before exiting through the stack. Throughout this process, the control room closely monitors emissions through a real-time continuous emission monitoring system, controls steam flow, and a number of other automated systems inside the facility.
Every day, tankers arrive and deliver byproduct, which is pumped into a reception tank and then a digester, where it stays for around 40 days, monitored all the while by a team of lab engineers on site. In the digester, microorganisms break down the byproduct into methane-rich biogas. This process is called anaerobic digestion, and it works in the same way that the body burns calories for energy, but on a much larger scale. The process captures a biogas, which consists of 60 to 65% methane, that is ideal for renewable energy production by fueling a 500 kilowatt biogas combined heat and power engine. This provides electricity and heat for the plant, and surplus electricity is exported to the national grid. Biogas is cleaned and upgraded to almost 100% pure methane, suitable for injection into the gas grid. Nothing for waste. After digestion, the byproduct is pasteurized at 70 degrees C for 1 hour, with leftover digestate returned to land as nutrient-rich fertilizer.
Household and industrial waste that is not recycled or recovered elsewhere is brought to the landfill site by truck. The waste is weighed and checked to make sure it is not dangerous in any way. It is then taken to a landfill cell. The design and location of these cells are thoroughly studied beforehand to make sure the environment is protected. Depending on the nature of the ground, the base and sides of each cell may be reinforced with an impermeable mineral layer. Then the cell is lined with watertight membranes to keep the waste mass contained. Waste is deposited in a cell in operation, then spread out and compacted. This operation is repeated, so the layers become increasingly dense as they accumulate. The rainwater that percolates through the waste forms a liquid known as leachate, which is drained off and treated. After a cell is filled to capacity, it is closed and covered with a layer of soil that is planted to ensure the site blends into its natural surroundings. The cell's environmental impact is monitored for several decades. Inside the airtight cell, an absence of oxygen causes the organic waste materials to ferment, a natural process that creates a large buildup of biogas, made up of a mixture of methane, carbon dioxide, nitrogen and oxygen. This biogas is captured by a network of vertical and horizontal wells that crisscross the layers of waste. It can then be used in a local industrial process or conveyed to a cogeneration plant. Next, the biogas is purified before being burned to fuel combustion engines. The combustion heat pushes a set of pistons, which in turn drive an alternator. This alternator produces electricity. Some is used on site and the rest is delivered to the high-voltage national grid. Residual heat from combustion can be transferred by heat exchanger to a nearby district heating network or to an industrial or agricultural facility. Capturing and utilizing biogas from landfill waste means less methane is released into the atmosphere, so it contributes to combating climate change as well as preserving resources. District heating replaces individual boilers. It uses less energy, costs less, is environment friendlier, and makes cities more pleasant places. Here's how and why at a glance. We generate the heat in boilers fueled by a variety of sources of energy. Most of them are renewable, biomass for example. And we also reclaim heat from waste incineration. That heat travels as hot water or steam through an underground pipe system. This is the primary circuit. Then it reaches substations in apartment buildings, office blocks, public buildings, and sometimes industrial districts or retail areas. Each substation has a heat exchanger that transfers the heat from the primary circuit to the secondary circuits in buildings. Inside, they split into heating circuits and hot water circuits. The heat then warms up the building, through underfloor systems and radiators for instance, and other appliances. The heating in these buildings is reliable, clean, quiet, and saves money. Once the water in the primary circuit has warmed up the building and cooled down, it returns to the heating plant, where we warm it up again. District heating systems combine renewable energies and digital technology to help to improve energy efficiency in cities and to make energy management smarter.
Low-income countries only collect about half of waste in cities and only about 1/4 in rural areas. There is much to be done in collecting waste in low-income countries.
Third, plastics are a profoundly difficult and complex problem.
26 million tons of plastic ends up in the ocean every year, where it becomes part of something much bigger. In the Pacific Ocean, plastic from America is swept into a large revolving ocean current known as a gyre. As this current circulates, it also picks up material from East Asia. Over time, these plastics accumulate in enormous flotillas. One of them is so big, it's even got its own name. The Eastern Pacific Garbage Patch.
In 2016, the world generated a whopping 242 million metric tons of plastic waste. We could make about 24 trillion plastic bottles out of it, and their water volume could fill up to 4.8 million Olympic-sized swimming pools. Even when plastic waste is collected, many countries don't have the capacity to process the waste, leading to dumping or mismanagement of it. Plastics in rivers, waterways, and oceans are a particularly growing urgent problem. 90% of marine debris is plastic.
The United Nations estimates that there's about 85 billion pounds a year of electronics waste that gets discarded around the world each and every year, and that's one of the most rapidly growing parts of our waste stream. And if you throw in other durable goods like automobiles and so forth, that number well more than doubles. And of course, the more developed the country, the bigger these mountains. Now, when you see these mountains, most people think of garbage. We see above ground mines. And the reason we see mines is because there's a lot of valuable raw materials that went into making all of this stuff in the first place. The metals we typically get from ore that we mine in ever widening mines and ever deep mines around the world. And the plastics we get from oil, which we go to more remote locations and drill ever deeper wells to extract. To put that in perspective, and I'm using steel as a proxy here for metals because it's the most common metal, if your stuff makes it to a recycler, probably over 90% of the metals are going to be recovered and reused for another purpose. And there's more plastics produced and consumed around the world on a volume basis every year than steel. They have very different densities, they have different electrical and magnetic properties, and they even have different colors. So it's very easy for either humans or machines to separate these metals from one another and from other materials. Plastics have overlapping densities over a very narrow range. They have either identical or very similar electrical and magnetic properties, and any plastic can be any color, as you probably well know. People, for as little as $1 a day, pick through our stuff, they extract what they can, which is mostly the metals, circuit boards and so forth, and they leave behind mostly what they can't recover, which is, again, mostly the plastics. Or they burn the plastics to get to the metals in burn houses like you see here, and they extract the metals by hand. Well, this is a photo I took standing on the rooftops of one of the largest slums in the world in Mumbai, India. They store their plastics on the roofs, they bring them below those roofs into small workshops like these, and people try very hard to separate the plastics by color, by shape, by feel, by any technique they can. And sometimes they'll resort to what's known as the burn and sniff technique, where they'll burn the plastic and smell the fumes to try to determine the type of plastic. So what are we to do about this space-age material, at least what we used to call a space-age material, this plastics?
This is the Padworth facility. You can see we're storing mixed bottles and recyclers here. This is the recycling process. And up there we're using the Magpie technology. Normally at a standard MRF, you just separate out the mixed plastics and they go to another facility to be sorted. What we're able to do here is to separate all the plastics out into the different streams. They're of much higher value if we do that, and you can recycle more materials. So here we're in the heart of the facility where you can see the material that's collected and stored. We pre-sort anything that shouldn't be there, and then we go through the magnet system, taking out metals, and then finally onto the magpie system, where we're separating out all the different plastics into the individual components. How it's set up is it shines a light onto the conveyor belt, and depending on what the plastic is, a different amount of light will be reflected back to the machine, and then it's calculating what is the most valuable and most frequently found plastic. So if it's looking at the belt and it sees lots of plastic bottles, it will shoot those plastic bottles off with air jets. And the rest of the material will go back round, and then something else will be more frequent and it will choose that material. With this magpie technology, we don't have to come in direct contact with the waste so much, but we still do need people in order to make sure the machine's working and to do the quality control. Finally, you can see the bunkers where we have the different materials stored, and they're baled and they go off to market. The magpie technology was developed by our R&D team in France, and there are 2 pilot facilities in France, and this is the first full application in Europe. It's a unique application of the infrared sorting, and it enables us to use one machine where normally you would need to use at least 4 or 5 machines. So it means we're more energy efficient, our carbon footprint's lower, and we're getting changes into the future, and different types of materials are manufactured. We can reprogram the machines.
The traditional way to make plastics is with oil or petrochemicals. You break down the molecules, you recombine them in very specific ways to make all the wonderful plastics that we enjoy each and every day. It certainly doesn't cost as much as oil, and it's plentiful, as I hope that you've been able to see from the photographs. And because we're not breaking down the plastic into molecules and recombining them, we're using a mining approach to extract the materials. We have significantly lower capital costs in our plant and equipment. We have enormous energy savings. I don't know how many other projects on the planet right now can save 80 to 90% of the energy compared to making something the traditional way. And we make a drop-in replacement for that plastic that's made from petrochemicals. Customers get to enjoy huge CO2 savings, they get to close the loop with their products, and they get to make more sustainable products. It starts with metal recyclers, who shred our stuff into very small bits. They recover the metals and leave behind what's called shredder residue. It's their waste. A very complex mixture of materials, but predominantly plastics. We take out the things that aren't plastics, such as the metals they miss, carpeting, foam, rubber, wood, glass, paper, you name it, even an occasional dead animal, unfortunately. And it goes in the first part of our process here, which is more like traditional recycling. We're sieving the material, we're using magnets, we're using air classification. It looks like a Willy Wonka factory at this point. At the end of this process, we have a mixed plastic composite, many different types of plastics and many different grades of plastics. This goes into the more sophisticated part of our process, and the really hard work, multi-step separation process begins. We grind the plastic down to about the size of your small fingernail. We use a very highly automated process to sort those plastics, not only by type, but by grade. And out the end of that part of the process come little flakes of plastic, one type, one grade. We then use optical sorting to color sort this material. We blend it in 50,000-pound blending silos. We push that material to extruders where we melt it, push it through small die holes, make spaghetti-like plastic strands, and we chop those strands into what are called pellets. And this becomes the currency of the plastics industry. Instead of your stuff ending up on a hillside in a developing country, or literally going up in smoke, you can find your old stuff back on top of your desk in new products, in your office, or back at work in your home. And these are just a few examples.
The average European junks about 525 kilograms of waste each year. I mean, that's a whole lot of stuff. And much of it really is stuff as opposed to waste. Useful stuff, worth money. All in all, it's just a waste of waste, isn't it? So what can you do about it? Okay, so you've got your half a ton of waste, which might not make you half a ton of money, but it could make you some. And off we go. A lot of the stuff in the bag is pretty useful as it is. Some bottles just need a wash up and a new cap. And old clothes and furniture come back into fashion before you know it. Some of it might need a bit of repair, but hey, that's job creation right there. Can't be a bad thing, can it? That's it, we're talking reuse. You might need to spend some money to make this happen, but since useful stuff is valuable, you'll get it back. and then some. Now, some of your waste might be useless in itself, but made out of good stuff, like metal, glass, paper and cardboard, all of which can be utilised again if you treat it right. And in fact, some of the really weird stuff used in electronic gadgets is so scarce that we actually need to use it again, if we don't want to run out. And yes, it's called recycling. Of course, collecting and processing isn't free, but here's the clever bit. Recycling turns your waste into useful stuff that can be sold. And as if by magic, new jobs will appear as well. Let's have a look at what's left in the bag. Food leftovers, used cooking oil, some wooden paper, lots of plastic and smelly stuff like cat litter and used diapers that sadly can't be reused or recycled. Or can it? Actually, it can. If you burn it to generate power and heat buildings, and collect the biogas to use as fuel, it might not smell of roses, but hey, this is useful stuff. Of course, you need to make some initial investments, but in the long run, burning waste is definitely a whole lot cheaper than burning oil or coal. Same with greenhouse gas emissions. No contest really. And then there's job creation again. This neat little trick is known as energy recovery. Not much left in the bag, is there? A whole lot less than half a ton, that's for sure. Time to get rid of what's left at that place we all know and hate. Sadly, it can't be avoided completely. Some waste is simply useless and won't even burn. Ah well. Of course, you don't want poisons lying about, so harmful stuff needs to be securely destroyed or stored out of harm's way. Safety first, of course. And there's job opportunities there as well. But hang on a second, do you really need to create that much waste to begin with? Come on, it's half a ton for crying out loud. Of course you don't. We could all begin by actually eating the food we produce. Today half of it goes into the bin somewhere along the line. I mean, that's just wrong. Another good idea is to steer clear of disposable containers and packaging. And why not try reading the paper online instead of on paper? And so on. The trick is to reduce the amount of stuff you throw away in the first place. So there you have it. And you know, the cool thing is that all this is being done all over Europe as we, or rather I, speak. For instance, in Norrköping, Sweden, 4 local fuel and power companies literally live off each other's waste. The stuff that one company discards becomes the next one's raw material. And round it goes. Brilliant! Meanwhile, in Hungary, a mushroom growing company have this really sweet sideline going. An electric power plant fueled by biogas made from mushroom scraps and used growing substrate that produces marketable green power. And in Cumbria in the UK, the county waste management people have worked with teachers and pupils to turn the Cockermouth School into a sustainable school. This is good news in more ways than one. Not only does the school chuck away a whole lot less than before, but the pupils have become expert reusers, recyclers and reducers in the process. And that's vital. After all, we're not born with sustainability skills. We all need to learn them. It's not like it's rocket science or anything, but still, knowledge is power. Green power. So, education and information is a big piece of the puzzle, no doubt. Costly, sure, but then again, you need to create jobs, don't you? I mean, let's face it, wasting your waste is such a waste.
So can we transform the world through ecologically intelligent design? To architect William McDonough, we must not only embrace new philosophies, but also innovative business strategies to reshape the world economy. His co-authored book, Cradle to Cradle, looks at how goods and services can generate not only economic value, but also ecological and social value.
The problem with recycling as we conventionally practice it or characterize it is that in most cases it's really what we've characterized as downcycling. The materials are losing their quality as they go through the system. We're calling for what we call upcycling. So it's either true recycling or even getting the product better. A bottle, for example, take a look at this bottle. This is polyester terephthalate. It contains antimony, which is a toxic heavy metal, as a result of catalytic reaction. catalyst that is used. This is idiotic because I don't need antimony in this bottle, and it's a beautiful material and can be infinitely reused. But right now, this will go off and become a park bench. It won't be reused as this. Plus, it's got this slightly toxic material. It doesn't affect you drinking the water, but it does affect the whole system. The system is contaminated by a carcinogen, which is just bad design. It's totally unnecessary. In order to be a living thing, you have to have growth, you have to have free energy from sunlight, and you have to have an open system of chemicals operating for the benefit of the organism and its reproduction. So what Dr. Michael Braungart and I are looking at with Cradle to Cradle is the idea that human artifice could follow the laws of life itself. And we would need growth, free energy from sunlight, and an open system of chemicals that are safe and healthy. So the real question becomes, when do we find ourselves in kinship with the natural world? When do we find ourselves as part of the natural world? And that's why Cradle to Cradle is so important. In nature, nature is not efficient. It's effective. So a cherry tree in the spring is not very efficient. Thousands of blossoms so you can get one tree to reproduce. It's not that interesting as far as efficiency goes, but it's magnificently effective. So we're looking at both human technology in terms of our comfort and our ability to thrive as a species, but also how would we integrate that into the natural world without destroying it? That's a fundamental question that we haven't asked as a species. We become part of the human resource of the natural world instead of simply seeing nature as natural resources of the human world. Well, Cradle to Cradle is a simple, commonsensical approach which says things either go back to soil safely and forever, or back to industry safely and forever. So we design products that we're going to end up in the dirt, like a paper plate. Why not design that with a little nitrogen in it so when you throw it away, the farmers want it? If we look at the products like cars or computers, those are things that want to go back to being cars and computers. So right now they become toxic waste. Why couldn't they go back into closed cycles? We see this happening as a small part of something really huge that's pretty much out of control.
Design today must reflect a new spirit. By employing the intelligence of natural systems, we can create industry, buildings, even regional plans that see nature and commerce not as mutually exclusive, but mutually coexisting.
The first industrial revolution was an aggregation of a lot of individual acts based on specific opportunity. It wasn't designed as a whole system. And now that we've seen the result of the whole system of the first industrial revolution based on brute force and the use of fossil fuels, we should stop, take a breath, or try to anyway, and say, wait a minute, was this designed? Was it our intention to release mercury? Was it our intention to cause climate change? Was our intention, to pollute the oceans? I mean, there's 6 times as much plastic as plankton in the Pacific Gyre north of Hawaii right now. I mean, did we intend that to happen? So the first industrial revolution was not designed. So when we call for industrial re-evolution, what we're looking at is to look at the whole system and say, if we could design a whole system of industry, how would we power it? How would we make things? How would we act? And that way we can have a vision toward which we can move a new industrial revolution. We're not asking everyone to become an expert at everything. We're asking everyone to understand that they could use the benefit of other people's expertise so that they don't become monolithic. Whereas what we're looking for is the best and the brightest coming together in multidisciplinary teams.
Implementing these ideas, we can design products that are continually recyclable and transform our current industrial system of take, make, and waste. Done intelligently, we would see as consumption increased, so would the health of the planet.
Living systems have been around for a few billion years and will be around for many more. In the living world, materials flow. One species' waste is another's food, energy is provided by the sun, Things grow, then die, and nutrients return to the soil safely. And it works. Yet as humans, we've adopted a linear approach. We take, we make, and we dispose. A new phone comes out, so we ditch the old one. Our washing machine packs up, so we buy another. Each time we do this, we're eating into a finite supply of resources and often producing toxic waste. It simply can't work long term. So what can? If we accept that the living world's cyclical model works, can we change our way of thinking so that we too operate a circular economy? Let's start with the biological cycle. How can our waste build capital rather than reduce it? By rethinking and redesigning products and components, and the packaging they come in, we can create safe and compostable materials that help grow more stuff. As they say in the movies, no resources have been lost in the making of this material. So what about the washing machines, mobile phones, fridges? We know they don't biodegrade. Here, we're talking about another sort of rethink, a way to cycle valuable metals, polymers, and alloys so they maintain their quality and continue to be useful beyond the shelf life of individual products. What if the goods of today became the resources of tomorrow? It makes commercial sense. Instead of the throw away and replace culture we've become used to, we'd adopt a return and renew one, where products and components are designed to be disassembled and regenerated. One solution may be to rethink the way we view ownership. What if we never actually owned our technologies? We simply licensed them from the manufacturers. Now, let's put these two cycles together. Imagine if we could design products to come back to their makers, a model that builds prosperity long term. And the good news is, there are already companies out there who are beginning to adopt this way of working. But the circular economy isn't about one manufacturer changing one product. It's about all the interconnecting companies that form our infrastructure and economy coming together. It's about energy. It's about rethinking the operating system itself. We have a fantastic opportunity to open new perspectives and new horizons. Instead of remaining trapped in the frustrations of the present, with creativity and innovation, we really can rethink and redesign our future.
Waste is growing, but so too is the global momentum to find solutions to stem the tide and make waste management more sustainable. Many solutions already exist. The World Bank is increasingly working with developing countries worldwide to invest in sustainable waste management and address challenges related to infrastructure, governance, financing, and capacity. For example, there are different ways to curb plastic waste by producing less, consuming less, and including plastic in overall waste management plans.
Solid waste data and planning are also part of the solution. It is important to understand how much and what types of waste are generated and where. This can help governments create more effective waste management policies and plans for the local context.
Waste management can be costly. It may be the single highest budget item for many local governments. However, it makes economic sense to manage properly. Uncollected waste and poorly disposed waste have significant health and environmental impacts. The cost of addressing these impacts is many times higher than the cost of developing and operating simple, adequate waste management systems.
In an era of rapid urbanization and population growth, solid waste management is a critical piece for sustainable, healthy, and inclusive cities and communities.
1.3 billion tons of food is wasted every year. If we were able to prevent it, this would be enough to feed all undernourished people in the world twice over. 15 to 20 million people around the world are working in the informal waste sector. If we could guarantee access to solid waste collection for all and controlled waste disposal facilities worldwide, those 15 to 20 million more could live healthier lives and have access to better services. By adopting environmentally sound technologies and methods, new green industries can grow, contributing to sustainable industrial development and job creation. In Europe, between the year 2000 and 2010, employment in waste and resource management doubled, reaching over 2 million. The estimate of the worldwide potential for new jobs in the circular economy is between 9 and 25 million. Now think of the environmental benefits that can be achieved. Integrated waste management has the potential to reduce greenhouse gas emissions by 15 to 20% across the economy, contributing to climate change mitigation. Sound management of waste can reduce the impact of natural disasters and help countries achieve climate resilience. What if we all change the way we think? What if waste isn't waste anymore? Having cleaner waters, cleaner land, cleaner air for all is possible and can become a reality. Rethink the way you waste. Be part of the change.
There is no longer any doubt that we will have to rethink the way we live on our planet. We already keep track of what we spend and buy at home, at work, in factories and in society. But what we don't do is keep track of the planet's resources that are being consumed more quickly than they can be regenerated. Instead, we need to rethink how to reduce, reuse, recycle, and eventually resource our way of living. Then it will be possible for 7 billion people, or even 9, to live on one planet.